Hello everyone. In this part of the lecture on analyzing the step response of the systems, our focus will be on determining some important parameters of the step response for the second order systems. From the previous lecture, we know that for the overdamped and critically damped systems, we can have approximations regarding the step response parameters, and especially for those two kind of second order systems, we will have only the rise time and the settling time, okay, because their response is somehow similar to first order systems. This is what we see here. For the critically damped systems, we have these approximations, and for the overdamped systems, we know that we can approximate them with a first order system, and then for the first order systems, we already know how to calculate the rise time and settling time. So for those two kind of second order systems, it's somehow straightforward. We just need to calculate or find the rise time and the settling time. However, for the underdamped systems, if you remember, the kind of step response is a bit different. We have some oscillations at the beginning, and then after a while, the response settles down. For this kind of second order systems, in the case of step response parameters, we define a couple of parameters which we didn't have before. The first one to define is called the peak time. The peak time, which is denoted as T_P, is the time required to reach the maximum peak, the first peak in it, okay, which is shown over here. So this is the time that it takes for the step response to reach its maximum value. And then we define the percent overshoot, or MP, which is shown also in the form of percentage OS, or overshoot. It's the amount that CT overshoots the steady state value at the peak time. Okay, so we find the maximum value that it reaches, which is the peak value, and then by looking at that, we can determine the amount of the overshoot, or percent overshoot. And it's indeed this amount. So this is the final value. This is the peak value. By finding this value over here, we will have the percent overshoot. The next parameter is let me first talk about the rise time, or TR. It is similar to what we had for the previous cases. The rise time is the time for CT to go from 10% to 90% of the steady state value, which is shown here. So here we have 10% of the final value. Over here we have the 90% of the final value, and the time that it takes for the response to reach that amount will be considered as the rise time. We also have the settling time here, T_S, which could be either 2% or 5% settling time. It's the time required for CT to reach and stay within a given percentage of the steady state value. And you can see it over here. So the steady state value is this value that we have here. And you can see that whenever the response enters into this area and then remains within that area, so you can see that first of all, the response enters the area here, but then after a while it goes out. Later it enters the area again, but then it goes out. And only at this point, T_S, the response enters the area and then it remains within the area. So prior to that, we had oscillations which were going beyond the area that we just are considering for the settling time. Therefore, TS, which could be defined for the 5% or 2% settling time, is defined in that way. So what you see here is the 2% settling time indeed. So the response enters into the area which is above 0.98 times the C final and below 1.02 times the C final. So in this way, the settling time is defined. Now we will see how to evaluate these values or these parameters. Yeah? So first let's start with the TP, the peak time. We know that it's the time in which the response reaches the maximum value. Therefore, we just need to find out, in order to find the exact time, we need to find the derivative of c and set it to 0. We can do the differentiation in this way. So we can use indeed the Laplace transform instead of the time domain expression for c of t. We need to find s times c of s. It will give us, if you take the derivative with respect to the time, it's equivalent in it to multiply the Laplace domain transformation by s. So we have s times c of s. And we can find s times c of s in this form. In it, c is equal to g times r, where r is equal to 1 over s. Therefore, s times c of s will be equal to s times g of s times 1 over s, which is indeed equal to g of s. And it's indeed equal to the impulse response of the system. On the other hand, if we have a look at the time domain derivative of c of t, we will get this expression, omega n over the denominator times this exponential term times this sinusoidal term. And then if we set the derivative to 0, we will obtain omega n times the square root of 1 minus zeta squared times t equal to n times p. Or we can say that t will be equal to n times pi over omega n times the square root of 1 minus zeta squared. And since the peak time is the first time that we reach the, let's say, local maximum, we just replace n with 1. So we replace n with 1 in order to obtain the t underscore p, which is equal to pi over omega n times square root of 1 minus zeta squared. So we just set n equal to 1 in order to find out the TP. So the peak time is obtained as pi over omega n times the square root of 1 minus zeta squared. Then we can have a look at the overshoot. We have the value for TP. We want to obtain the value for the percent overshoot, which could be calculated as 100 times C max minus C final over C final. Okay. For the system that we are considering, the DC gain is equal to 1. As a result, the C final will be equal to 1 as well. Therefore, we just need to find out the value for C max. So we will have C max minus 1 over 1. Or 100 times C max minus 1 will give us the percent overshoot. How can we find C max? We already have the value for TP. We can replace the value of T with TP in the expression that we have for C of T, and out of that we will get the value for C max. The expression for CT is written here. You can check it out how it is obtained by looking at the previous lectures. And if we substitute T with TP, for which we have found the value in the previous slide over here, so 1 pi over omega n times the square root of 1 minus zeta squared, we will get the C max. The value for C max, which will be obtained after simplification, it will be obtained as 1 plus e2 minus zeta pi over square root of 1 minus zeta squared. And we also know that the C final is equal to 1. So we need to find out 100 times C max minus 1. If we do the subtraction, we will get 100 times 1 plus e to the power of minus theta pi over square root of 1 minus theta squared minus 1. And then we will get 100 times the exponential term, e2 minus zeta pi over the square root of 1 minus zeta squared. And that's what you could see over here as well. Something important to notice here is that MP depends only on the value of zeta. You don't see omega n here, yeah? So MP is only related to the value of zeta. We have here the expression of MP in terms of zeta. We can have zeta expressed in terms of MP as well, and that's what you see here. Minus ln of MP over 100 over the denominator. And we can also draw the MP versus zeta. By looking at this, you can see that as the value of zeta decreases, as zeta goes from 1 towards 0, the value of MP, the overshoot, increases from 0% towards 100% at the limit. So when zeta is equal to 0, the overshoot will be equal to 100%, and that's what we have for the undamped systems. So over here we have the undamped system. When zeta becomes equal to 1, the overshoot will be equal to 0. And you should remember that zeta equal to 1 is indeed what we have for the critically damped systems, where we don't have any overshoot. So this is quite important to keep in mind. MP is related or is proportional to kind of 1 over zeta. As zeta increases, MP decreases, and vice versa. The next parameter to evaluate is the settling time, Ts. In order to find the settling time, we need to determine the time for which C of T reaches and stays. So it reaches and stays, this is important, within plus minus 2% or plus minus 5% of the steady state value, or C final, which is equal to 1 for our case. We can have a look at the expression that we have for the C of T in the time domain, for the response in the time domain. It's in the form of 1 minus a coefficient times an exponential term times a cosine term. We are interested in finding some approximate value for the settling time instead of finding the exact value, which might not be straightforward to do. In order to do that, if we look at the curve that we have for the step response, you can see that it's in this form. There are some oscillations at the beginning, and then after a while it just settles down. On the other hand, if we draw this term, one minus e2 minus j omega n over square root of 1 minus zeta squared. That's what you see over here as well. We will end up with this. Okay, so this is the graph that we get. If we draw the 1 plus e2 minus zeta omega nt over square root of 1 minus zeta squared, which is over here, we will end up with this graph. And these two graphs are in some sense are kind of envelope curves, meaning that the actual response that we have for the system will always remain between these two envelope curves, these two graphs. So it will never go beyond these. In it, they somehow create a zone in which the actual response of the system will remain in that zone and it will not go out of that. Okay, and since we have them in the form of a kind of response of a first order system, we can kind of approximate the settling time for the second order system by looking at these envelope curves. Okay, so we kind of define the time constant as t equal to 1 over zeta omega n. So this will be the time constant for a first order system, which would give us a step response similar to what we have over here. And then now we can have an approximation for the 5% settling time and 2% settling time, referring to the first order systems in the form of 3 times the time constant or 4 times the time constant. And then we will have 3 over zeta omega n or 4 over zeta omega n. Now we can sum up. This is the kind of evaluations that we have for the step response parameters of the underdamped second order systems. You know how to do it for the critically damped and overdamped systems. We have the expression for TP, for the peak time. We have it for the percent overshoot, 5% settling time, 2% settling time, and we can also approximate the rise time as the expression that is shown here, 1.8 over omega n. Okay, so for now you just keep in mind that rise time is given in the form of 1.8 over omega n. If you want, you can also, we can show how this is obtained, but for the purpose of this course, for now it's enough to have this expression. Alright, now we can have a look at this example. We have the transfer function given for a system in the form of 100 over s squared plus 15s plus 100, and we want to find out the values for peak time, MP, settling times, and the rise time. What we need to do here is to find out the omega n and zeta values. Okay, if we compare this with the general expression that we have for a second order system, we can see that omega n squared is equal to 100, therefore omega n is equal to 10, and 2 zeta omega n is equal to 15. If I replace omega n with its value, we will get 20 zeta equal to 15, and then zeta will be equal to 15 over 20. 3 over 4 or 0.75. So zeta will be equal to 0.75 and omega n is equal to 10. Now we can have a look at the expressions that we have for our step response parameters. For TP we will have pi over 10 times square root of 1 minus 0.75 squared. For MP we will have 100 times the e2 minus 0.75 times pi over square root of 1 minus 0.75 squared. And similarly for the settling time and 2% and 5% settling time and the rise time, you can replace the values for the zeta and omega n and then obtain the parameters for the step response. For the rise time, you should also keep in mind that rise time increases as omega n decrease and vice versa. They behave somehow in a similar way that we had for the overshoot and the zeta. When one of them decreases, the other one increases and vice versa. Okay, so that's all for this lecture. In the next lecture, we will go through the relation between the position and the parameters, step response parameters of the second order systems. Thank you for watching this lecture.